So in this lab, we sort of built upon the principles that were explored in the previous lab. So similarly to the previous lab, we have two pieces of charged tape, um, and we have the gravitational force pointing downwards, and we're accounting for an electric force pointing upwards. The tapes are still the same zero point 0.2 meters long, and the main difference here is that we are more accurately representing the charge on the tapes themselves. Last time we were representing it by a point charge in the center, and we sort of averaged out the charges. But this time we are representing it as a distributed, evenly distributed charge across the entire length of the tape. And so in my experiment for this, the top tape floated about 3 centimeters or 0.03 meters above the bottom tape. The tapes are each 0.2 meters long, and they weigh about 0.0002 kilograms. So the gravitational force comes out to be this 1.962 times 10 to the negative 3 newtons, and it's pointing downwards, as you can see, represented by this yellow arrow. And conversely, the only other force acting on the tape in this model is the electric force. So you can see that represented by this white arrow, and it must be equal and opposite to the gravitational force in order to keep this tape floating. So the net force has to cancel out to zero in order for the tape to stay at rest. And from this model, and from the understanding that in order for the tape to float, the electric force must be equal and opposite to the gravitational force, I was able to determine the magnitude of the charge on a piece of tape. And it came out to be this 5.80403 times 10 to the negative 9 coulombs. Now, even though this model is much more accurate than the model from the previous lab, since we didn't treat the charge of the tape as a point charge, there were still some assumptions that had to be made about the experiment in order to model it like this. First of all, I completely ignore air resistance, which would reduce the electric force required to keep this tape afloat. There would be a secondary arrow here pointing upwards, and what would happen is that instead of the gravitational force having to be equal to the electric force, the gravitational force would have to be equal to the electric force plus air resistance. So ultimately, this electric force would be decreased. And the second assumption that I made was that each tape has the same charge and that the charges are evenly distributed along the entire length of the tape. And that's not entirely accurate either, because it's still possible, for example, for the bottom tape to have a significantly higher charge than the top tape, and for the equation to still work out that we have the same electric force on the top tape. Or for some of these charges along the tape to vary, not be exactly the same across it, and the for the electric force to still add up to the same 1.962 times 10 to the negative 3. Overall, though, it's still much more accurate, a much more accurate representation than what we produce in Lab 1. And thank you for listening to my lab.